Hello everyone. In this session, I'm going to look at building classification trees where the response variable is binary. In my earlier session, I have looked at the classification trees where the response variable has even greater than or equal to two categories, wherein you could have used the simple tree algorithm or C 5.0 algorithm, or we could have used evolutionary tree kind of algorithm, conditional inference classification tree algorithm, or we could have used even an oblique tree kind of algorithm. All of these trees algorithms are very much suited if your dependent variable is having two or even more than two categories. But here what we are going to look at is the classification trees where the response variable is purely binary, only two attributes associated with the response variable, right? So in this context, I want to bring out two major algorithms. One is the logistic model based recursive partitioning algorithm, and the other one is probit model based recursive partitioning. So these are the two algorithms that we are going to look at. As we have discussed even in our earlier session, the focus is on applying these algorithms to a data set rather than spending a lot of time in terms of discussing the mathematics behind these algorithms or spending more time in terms of deriving the formulas behind these algorithms. Here our focus is more on using a tool like R, a statistical package like R. Within this R, using an appropriate package to perform logistic model based recursive partitioning on a training data, use that model to test it out on the testing data and try evaluating the accuracy of the model before rolling out to the new data altogether. So that's the kind of a process that we are going to follow, right? For both logistic model based recursive partitioning as well as probit based recursive partitioning. So let's get started. So this is a model where the recursive partitioning is simply performed. The entire logistic regression tree is typically built. The tree that is built here is a logistic regression tree, which can be accomplished with the same party package which we have used even for our conditional inference classification tree. The logistic model based recursive partitioning also can be done using the party package, but we will use the mop function there instead of the typical C tree function that we have used for the conditional inference classification tree. So I think that library should already be there. So the data wise, again I'll be using the same data set that we have used for more than two, but because this is binary, I'll do some small modifications to this data. Let me look at the summary of this data, India. Here, result wise, I could see there are 64 lost, 98 wins, but 4 are tied. What I want to do is I'll remove these 4 tied from my data so that only the remaining where where only two outcome variables will be there, and we can use both binary logistic model based recursive partitioning as well as the probit model based, because these two algorithms are majorly targeted towards the response variable being a binary variable. So I'll create another variable called India1, wherein I am taking a subset of India, where I will take India dollar result, right? India dollar result I'm setting it not equal to tide. India dollar result not equal to tide is what I'm setting as India 1. Oh, I have to set even the column number. I'll take all the columns. So that is what is my India 1. Now let's look at the summary of this India 1 to understand the data better. Okay, tide is coming out to be 0. It's better that I remove it altogether from the model itself. Looks like it is removed. The overall it is only 162. Right? So India 1 does not contain anything from India where the tide as a variable is lying. Alright, let's try it out. So this is what is my data set altogether. Right? So we'll go with this particular data set for this exercise. The function that we have to use is mob. So let me load the library package first. The party package. Let me load it. So the party package is loaded. I have to use a mob function for performing this logistic model based recursive partitioning. So the mob function, it's an algorithm for a model based recursive partitioning. So here we are using a logistic model based recursive partitioning, and after this we are going to look at a probit model based recursive partitioning. So for a model based recursive partitioning I can use this mob algorithm. It will give me a tree with fitted models. So there is a model at each terminal node. There is a formula or a model that is created for each terminal node. So there is a partitioning of the tree that is happening, and once the tree is partitioned, there is a model that is created for each of the terminal nodes. The way I specify here is I am giving a formula, but here the formula is a slightly different formula. Right? You could see this should be of the type y, which is my response variable, tilde x1, x2, xk, which are the variables, one set of variables, z1, z2, z3, zl, where there are two sets of variables here. So the variables before this sign, they are passed to the model. So my model formula will be created based on those variables x1, x2, xk. Whereas the variables that are after that vertical line, they are used for the partitioning purpose. So the tree will be built based on the variables that are given after, whereas the formula will be built based on the variables that are given before the vertical line. That's the way I have to give the formula out here. Then I am giving the data. See here, the data is in the form of a list. It's a data frame containing the variables in the model. So I can very well give the data frame as an input. But the most important part is the model. The model here, by default it's a G linear model, right? Whereas the model can very well be specified from this stat model. So you could look at the details here. So fit a model. So the default is a stat model out here, and if you look at the stat model, I can very well give all these things, right? I can very well split something like a stat model out here. So different kinds of stat models can very well be fitted out here when I'm using a G. So by default it is a G linear model. And the most important part here is I will specify the family to which this particular model will belong to, and for each one of them I can specify a different family altogether. Right, in the stat model I can very well specify the family associated with this. Probably you could see here I can give a control talking about what should be the minimum split. The model is a linear model or a generalized linear model. If I give G linear model, it becomes a generalized linear model. And within that generalized linear model, I can very well specify the family of the models that I would like to look at. You see here partitioning, logistic regression database. So the model is G linear, but family I will set it equal to binomial. So I can very well set the family like this, which can help me in terms of doing the recursive partitioning quite comfortably. So here Z is a binary response variable. I'll use the result variable here. XYZ are conditioning covariates. So those variables which I want to be there as a part of the model, and ABC are the ones that are the partitioning covariates, the variables with which the tree will get partitioned. The model is a G linear model, which is what we are calling as a generalized linear model. And if I set family equal to binomial, then I'm setting it as a logistic model based recursive partitioning. So that is what we will try to do. Initially, we have loaded the party package. We got the data. Identify which variables will be used as a conditioning covariates. Yes. Now I will create a formula F, right? Probably here, because it's a new thing. First of all, I have to break the data also into training and testing. So, but first let me set F, which is the formula that I want to create, right? The formula that I want to create, wherein I'm considering the result. So let me load the names of India 1 so that I'll use them properly. Okay, so the formula for me is result tilde the variables which I want to be a part of the model. I'll use score as one variable. Innings I'll use for the partitioning purpose. Depending on the first innings and the second innings, I want a different score. Opposition, probably for each opposition, if I want a separate model, then I'll put it as a part of the partitioning. But otherwise, I can treat it as a part of the model. Let me treat it as a part of partitioning. The venue, away versus home, also I'll keep it as a part of partitioning. The runs, I'll treat it here. The proportion of runs also let me treat it here. Status, I don't want to consider whether it is out or not out influencing. The strike rate, let me consider it here. The position at which he bats, also let me consider it as a part of the model along with the entry score. So all these things will be there as a part of my conditioning variables. Whereas I will consider the innings for partitioning purpose. So I'll have different partitions for different innings. Similarly, the opposition also let me consider for time being as a part of partitioning variable. Venue, home versus away, even let that be there as a part of the partitioning purpose. Right, so this is the model that I would like to create here. So there are 3 variables that I am using for partitioning purpose. There are 6 variables that I am using for model building purpose. So that's the formula that I am creating out here. Now I have to see how many observations are there. Right now we have 4 reduced. So I will say n row of India 1, which is telling me that 162 observations are there. Out of that, if I take 70%, which is approximately 113, right? So I'll set a seed, let's say of 1000. I will consider, right, train, wherein I am taking a sample 1 to n, out of this 1 to 162, select this 113 elements, some 113 elements randomly, where the replace equal to false, where there is no duplication of the element, which is giving me that these are the values that go as a part of the train. Now I can very well consider my train data, which is nothing but it's a subset of India 1 containing the train rows and all the columns, and my test data is again a subset of India 1 containing minus train data and minus train rows and all the columns. So I have the number of rows, training data, testing data, and even a formula is there in place. So I have done some preliminary inspection of the data. If there are NAs, we will remove, but in this case we don't have even NAs, so I don't need to bother much about it. I have split the data randomly into a training data and a testing data, so even that part has been taken care of. Now comes the estimation part. So let me use fit underscore logistic model based recursive partitioning. Logistic. I'll simply use fit underscore logistic model based recursive partitioning, where I am using the mob. The F is the function that we have created, the formula that we have created. The data, I can very well take it as train data. That is the one that is used for building the model. And we have said that the model that we have to use here is the G linear model. Right? I should not use linear, I'll use the G linear model. And because I'm using it as a logistic partitioning based model, I'm setting the family as binomial. Logistic model based recursive partitioning is what I'm doing here. So I'm setting it as binomial. Now you could see there is a fit. The fit logistic has taken care of fitting a model to this data. Let's see what the fitting has been taken care of. So I could see here for venue equal to away. Okay, it's only built based on home and away. It did not build even based on the innings. Right, that's one thing we have to be understanding here. So the venue is away. There are 72 such kind of observations, and these are the coefficients associated with away. So this much times score, this much times runs, proportion, the strike rate, the position, and the entry score. Whereas in case of home, we got a slightly different kind of a model. That is what has been fitted by my fit logistic. I can very well do a plotting of this particular model also. The plotting has given me this kind of a tree structure. Right, for away only I've got this. Right, for the home I did not get anything appropriate. Right, for the away, this is what is the data that we have got. So for node 2, so we are able to see that in case of away, right, in case of away, we could see that this is typically growing. Right, we could clearly see that as the runs are increasing, as the score is increasing, we could see that the chances of winning are increasing. Right? As the runs are increasing, the chances of winning are also increasing. And at the same time, if I'm looking at the other ones, even with respect to the runs that are scored by Virat, as the runs are increasing, the chances of winning are also increasing. So similarly, as the proportion of runs he is scoring is increasing, the chances of the team winning are also increasing, and so on. The same logic is going for the last one as well, the strike rate. As the strike rate has increased, the chances of winning are also increasing. So that's the way we could see the plotting of this logistic regression out here, right? So we have used the plot to visualize, and what we have got is typically a spinogram. Fitted lines are the mean predicted probabilities in each of the groups. So we are getting the fitted lines for each of the groups. So we are getting them as the mean predicted probabilities for each of the groups. So if I look at this, this is how my graph has come out. Right, the graph did not come out properly because of so many variables being involved in the process. But what we could see is majority of the variables, as the value is increasing, even the chances of winning are also increasing in the process, right? So because the graph did not come out much proper, I would like to look at directly the formula, the coefficients, etc. That is much more appropriate for me to understand the process. So I could very well look at the coefficients of this particular model. For the coefficients of this particular model, if I am looking at, okay, there are two major cuts out here. One is we are talking about away as a venue, the other one is home as a venue. So in case of away, this is what are the coefficients: minus 1.91 plus 0.01, so on, so on. Right? If I can do even a summary, I will get this result. When I am doing a summary of the model, this is what is very important for me to understand here. This is for node number 2. The formula is like this, with a standard error of this much. You could see here probably the probabilities wise, yes, score is slightly significant because p value is lying between 5 to 10%. Now you could see here, if the p value is 0, it is very highly significant. 0.001, the next slightly less significant. 0.01, which is around 1%, even less significant, minutely significant, and just very, very nominally significant if it is between 0.5 and 0.1. So a small dot indicates that the significance is there, but very, very minimal significance for proportion as well as the score. Whereas the position at which he is batting is very, very significant in terms of deciding whether the country will win or not. And the score at which he has typically entered the crease is even more significant because it has 2 stars that are built into it. This is when we are talking about the away series. And that too, the higher is entering, because this is positive, the higher the score at which he is coming to the crease, the higher are the chances of the country winning. Whereas in the position, the higher he is coming in the order, the lower are the chances of winning because the coefficient is negative. So if he is coming to bat very early on, the chances of the country winning are much higher in the away scenarios. And the higher is the strike rate at which he bats, the higher are the chances of winning. The higher is his proportion over the total score, the higher are the chances of winning for the country. And the higher is the country's score, the much higher is the chance of winning in the abroad series. And here we could see that the AIC, which is a kind of a mechanism for comparing the different models, is around 96.046. We'll talk about it. Right, so that is what is for the away series. Now look at the home series here. So this is what is the situation in case of home. The score is looking negative out here, but look at the significance. It's only the position at which he is batting is slightly significant. All other things are insignificant, which means in the home series, probably many other things are contributing to the victory of the country. Whereas in the away series, it is looking very clear that his contribution is playing a major role in terms of the country successfully winning that particular game. So we are getting the coefficients at each of the layers. So in this case, the AIC is just 43, which is indicating that the error part is much lower. And now overall, if I have to look at the log likelihood, one of the mechanisms that is used for assessing or comparing the various parameters, I can use the log likelihood associated with this particular model, which is telling me minus 55. So if any other model is giving me a log likelihood much higher than minus 55, let's say minus 40, minus 30 something, that would be a more preferable model for me compared to this particular model. And similarly, I could also look at the AIC of the model, which is also another different way of measuring the error. So the overall error rate is around 141. I want this value to be lesser if I have to use any other meta model for this particular purpose. Now, if this is the model that I am going with, then I can do the prediction here. Pred underscore logistic is the prediction that I am performing. So I'll use the same predict function. The model that I am using is fit logistic model. The new data that I am using is my test data. So all these things will still continue the same. I will go ahead with this as the pred logistic. But the thing is, the pred logistic, if you see here, it gives me the probabilities, right? It gives me the probability that the value belongs to group 1. So this is where I say if else. I'll use a simple if else. So let me use pred or pred category, pred cat. So I'll use a simple if else function saying if this pred logistic is less than 0.5, take it as lost, and if it is greater than, take it as 1. So set it like this. If it is greater, take it as this, then lesser, take it as this. So you can very well take lost and 1. So you are getting your pred category now. The pred category is working out to one loss kind of stuff, right? Or probably instead of saying, okay, let's try it out, right? So we have created this kind of a table. So then we'll take a table from the actuals itself, test data dollar result, comma pred cat, and you can very well take the DNN as actual and also predicted. Okay, so now in this case you could see lost versus 1. Here it is 26 that are correctly predicted. Forget about tide. Tide is not there as a part of our model at all. So it is saying 26 as accurate prediction, 23 are faulty predictions. So the accuracy is working out in this case as 26 divided by 49. 26 divided by 49 resulting in 53% accuracy going with this specific model. If I'm using the logistic model based recursive partitioning, the accuracy is coming out to around 53%, Whereas if I'm using, I have to try if there is any other model which can give me a much better representation of the overall model. Right, because we don't have too many options as a part of this. The only thing is now I have to try changing out the variables. Right, I have to change my function. Let me try one such changing of the function. Right, let me try changing the function a little bit. So the f, let me try changing it. Result, I'll take them based on all these things, but I have to consider. So we'll see if runs is very important. So we have to really test out. We need to have a subject knowledge. But let's say based on the data that we have got, that particular variable that has not been contributing at all, right? Probably the runs that he has scored looks like it did not contribute in any one of them, and even the strike rate did not contribute. So let me just remove the strike rate from the whole calculation and let me redo the process. That's it. I won't change anything much. My formula I have just changed, removing only the strike rate from the whole thing. Now we'll go ahead in terms of fitting the model again. Right, I'm fitting the logistic model with this. The same thing I'm continuing. Then I am going ahead in terms of seeing what this model is all about. So I'm using fit logistic. So here also it's coming out that with respect to the venue only away versus home, that's the only thing that we have got. Even when I am doing the plot, I don't think things have changed anything better out here. Plot is coming more or less similar. It's only the strike rate got removed in the overall process, right? Then once I have got the plotting of this particular model, I can very well look at the coefficients if I want. Otherwise, I'll directly get into the prediction. Let me look at the log likelihood to see if this model is anywhere better compared to the overall, the initial model that we have considered, including the strike rate. The log likelihood became minus 56, whereas in the earlier case the log likelihood was minus 55. So because this is lesser than the earlier case, this is not a good model. Similarly, when I am looking at AIC of the model also, AIC is 139, whereas in the earlier case I've got AIC as 141. Okay, the AIC looks like it has come down. So I can very well think of using this particular model also. But much more before that, let me try going ahead with doing the prediction with this particular model. We have done the prediction. Then let me build the predicted category based on this. Okay, the predicted category is being done, and go ahead in terms of doing the testing between the actuals versus the predicted. If I go with a table, so this model says that 27 out of 49 are accurately predicted, increasing the accuracy of the model to 55. So we can try playing around with the stuff to really try to understand what is the kind of logic that is associated with classifying each of the values into either won or lost depending on the various values that are being provided as the different predictors for the model. So let me quickly read through it. I can even get the cumulative density function also for this. Interpretation can be drawn from the plot, or I could also have done the coefficient estimate. That's where I have used the coef function to get the coefficient estimates for each one of them. So we could clearly make out which variables are significantly impacting and which of them are not significantly impacting. Let me look at a summary again of this particular model to see what is the improvement this time. Even this time here runs are not contributing in case of away. What are the runs? So the score, the proportion are sufficient enough, right? And in case of category 3 it looks like nothing is contributing. So this is where in case of home probably neither the runs that he has scored, neither nor the proportion of runs, nothing is really making the position at which he comes to bat. Nothing is really creating any kind of significant impact in terms of India winning the game. Whereas when it comes to the away series, it's very clearly visible that his contribution is very well required in terms of India winning the games, right? So that is one thing that we are able to derive out of this particular model. So we have compared the models using the log likelihood and Akai information criteria. The log likelihood value should be higher, the higher the better, whereas Akai information criteria says the lower the better. So we have done the prediction based on the model to the testing data. We have set the appropriate threshold 0.5. So we have used if else kind of a function. If the predicted probability is less than 0.5, then categorize it as lost, and if it is greater than 0.5, categorize it as 1. So we got the confusion table, and based on that we have looked at the misclassification error. So that is what we do as a part of the logistic model based recursive partitioning. Moving forward to the next one, which is a probit model based recursive partitioning. Let me tell you, everything is exactly same as the logistic model based recursive partitioning. The only difference is the family that we are giving. Right, the function, everything is the same. It's only the family. Instead of specifying just the binomial, when I specify it as just the binomial, we are getting it as a logit function. That is logic distribution is typically used internally, but if I want a probit model, I have to explicitly specify that link is equal to probit. Rest of the things are exactly the same. So what I would like to do is I'll directly use fit underscore probit, wherein I am directly using the mop function. F is my function that we have created. The data is train data, that is what we are using for building the model. The model for me is again G linear model. The family this time is also a binomial, even there is no change out here, but the only difference is the link is something that we are specifying as probit. If I don't specify any link, it will be taken as logit, and we will get the logistic model based recursive partitioning. Here I am using the probit. Where did I use double? Okay, so here the name is looking slightly odd. Underscore is something that I have to use out here. Yes, the model is this one. When I look at the fit probit, let's see what is being used for fitting purpose. Even here it went with the same scenario, right? Venue is away versus home. This is the typical equation that it was able to create both for away as well as for home. We see there is a small change in the equation. If you just see here, right, in case of home the equation is minus 1.8, whereas here it works out to minus 1.1. Score is minus 0.01, so it looks slightly similar. Runs is minus 0.001 here, whereas it is 0.007. Proportion has 14% out here, whereas it is only 8. And that way there is a difference in the way the model got built. But yes, this is the model for me. I can do a plotting of this model to understand. Right here also, because the variables are too many, the model can get complicated, but one thing is looking much comfortable. The higher is the runs or score or whatever it is looking in, the higher the chances of victory. That is what even my logic model has given. Even the probit model is giving me the same. And I can very well take the coefficients, or probably it's better that I take the summary of the model to understand it much better. So the for category number 2, the model is like, okay, score is very much important in the away. So overall, how much score the team has scored. The proportion of runs scored by Virat Kohli makes a small impact, but the position at which he is coming to bat is a decent impact, and the entry score at which he is coming to bat, the higher the entry score at which he is coming to bat, the higher is the chances of winning for the country. So that's how the score came out. And even in case for the home series, it looks like similar. None of the things are really significantly influencing, right? None of them are significantly influencing the country winning in case of a home series. That is what we could see. None of the variables are typically marked with a star. But if I have to compare between the logic model and the probit model, I can very well consider the log likelihood. Here the log likelihood is minus 56.5, whereas in the earlier case looks like the log likelihood is minus 56.78. It looks like a very minute improvement in the log likelihood value. Similarly, when I am going with a Kaike information criteria for the same, it's also in the range of 139. So I don't see too much of a big difference between these two models, right? And I could go ahead in terms of prediction underscore probit, where I am looking at the predicted value. We'll use predict. The model is the probit model, fit underscore probit. And the new data for me is the testing data, so I'm calling it as test data, and that's it. Now using this, there is a prediction that is being performed, and predcat, I'll take a predicted category where I'm using if else function, where I'm setting if the predicted probability is less than 0.5, select it as lost, else take it as 1. So that's the kind of a breakup that we are doing, and based on that I'm creating a table. The actual is test data dollar result, whereas the predicted one is predcat. The DNN I'm setting it as a C variable, a C function, where I'm looking at actuals versus predicted. So in this case also 27 are accurate. So 27 out of 49 giving me around 55% accuracy even when I am going with the probit based model itself. So both the logic based model as well as probit based model for this kind of a data set, they are resulting in more or less similar layers of accuracy, but the formula is slightly different. So the percentage, the probability of an observation being falling into each of these categories looks slightly different in both. So if the cutoff value changes, there is a good chance that the overall classification, overall classification of the data could be different in both the models. So we have to really start understanding the model more and more in depth, the variables that could really contribute to the winning of a particular country, and based on them we have to keep improvising the models so that when we are doing a testing on the test data, the accuracy of the model typically goes up quite drastically. So these are some of the things that we have to keep in mind. So process wise, I think it's the same thing. We have loaded the package, got the data, we have identified which variables will be conditioning variables and which one will be used for partitioning. We have done the basic inspection of the data, split the data into training and testing data. We have used the estimation of the model, the probit model. The only difference is we will add this one single point within the family in the mop function. We have got the coefficients of the model. Then we have taken a prediction on the testing data using the model, and based on that we have set the cutoff as 0.5. If the probability is less than 0.5, we will categorize it as lost, otherwise we will put it into the one kind of a group. Based on that, we have looked at the confusion matrix as well as the misclassification error rate or the accuracy rate of the model. So this is what I wanted to cover as a part of this session. We have spent two different models which are more or less similar with a very minute difference between them, especially if I have to address the problem of classification using binary variables only. Note the earlier models that we have used, the tree-based models that we have used earlier in the previous session, they all can be used for binary data. But let me tell you, these two models cannot be used for the data which have more than two categories. So that's where the limitation is, and that's the reason I have to take these two models separately as a different session altogether. If you have any further queries regarding the understanding of these two models, please feel free to get back to me by giving me a call on the number that I have given below, or you can send in an email at vamsidhar@facegurus.com. Thanks a lot for listening to this session. Thank you very much.